the electronic effects of the first year basic organic chemistry. The last effect, electronic effect that we are studying is hyperconjugation effect. In this hyperconjugation effect, we consider this carbon hydrogen sigma electrons interaction with pi electrons of adjacent multiple bond, giving rise to the or we can call it as CH sigma electrons interaction with pi electrons of adjacent multiple bond is called hyperconjugation effect. Now let us consider, this was actually proposed by Baker and Nathan. That's why it is also named as the Baker-Nathan effect. Okay. Now let us consider this explanation of the hyperconjugation effect by considering suitable examples. Suppose I have this CH double bond CH2. This is propene. When we consider this carbon atom, this is actually called alpha carbon atom. If one hydrogen atom of the alpha carbon atom, the sigma electrons of this carbon hydrogen sigma bond interacts with this pi electron, then we have this CH, then this sigma electron shifts to this position, double bond CH, and this CH2. This will carry negative charge. So this sigma electron will shift to this position. But this hydrogen atom, losing the electron density, will get the positive charge, but still remains close to this ion. So this structure is actually named as the hyperconjugation structure, just like the resonance effect or mesomeric effect. But in resonance effect, we consider the interaction of the two multiple bonds or interaction of the multiple bond with lone pair. But here it is the sigma electron of the carbon hydrogen alpha carbon atom interaction with the multiple bond. Similarly, for this second hydrogen we can write H plus CH double bond CH CS2 minus. Similarly, due to this third hydrogen we can write HCH H plus double bond CH CS2 minus. So these three resonance structures obtained due to interaction of this sigma carbon hydrogen electrons or electron with the multiple bond are called as the hyperconjugation structures. Whatever is the number of alpha hydrogen atoms adjacent to this carbon-carbon double bond, that many kinds of hyperconjugation structures we get. Okay. Similarly, let us consider one more example. Suppose you take this CH3, then one more carbon CH3, CH double bond C double bond CH2. Now this contains 3 alpha carbon hydrogen bonds. This contains 3 alpha carbon hydrogen bonds. That's why totally 6 hyperconjugation structures are possible with one original one. Similarly, in this case it is 3 hyperconjugation structures plus original one. In this case it gives rise to 6 hyperconjugation structures plus 1. Suppose I write this CH3, CCH3, double bond, CHCH3, CH3. Sorry, CH2 I will write. CH I will write. Since this is alpha carbon, this is alpha carbon, this is alpha carbon. Totally 9 hydrogen atoms are there in the alpha position. That's why this will give rise to 9 hyperconjugation structures. Plus 1 original. Similarly, if you take this CH3, CCH3, double bond, CCH3, CH3. This contains 12 alpha hydrogen atoms. That's why it gives rise to hyperconjugation structures, 12 plus 1. What we observe here is, larger the number of hyperconjugation structures, greater will be the stability of that particular compound. So it is this compound more stable than this 9 hyperconjugate structures, more than 6, more than this 3. But if you take only ethene, CH2 double bond CH2, it does not possess any hyperconjugation structures. Now let us see the effect of these hyperconjugation structures. In case of these aromatic compound containing alpha hydrogen atoms. This is actually toluene. In case of this toluene, there are only 3 alpha carbon hydrogen bonds. That's why we can write these hyperconjugation structures CH, and this will carry H plus, and this will interact with this double bond to give rise to, I will write this CH, and one of the hydrogen alpha carbon sigma electron interacts with this multiple bond. That's why we have this negative charge on this one. This will further undergo resonance effect to give rise to 2 more structures. So we have this double bond CH and H plus, double bond here, negative charge double bond, because of the interaction with this. So this will again undergo interaction like this to give rise to 1 more such structure, double bond H plus. In case of the toluene, for 1 alpha carbon hydrogen sigma electrons, we have these 3 hyperconjugation structures. But because of the 2 more hydrogen alpha carbon atoms, so we have plus 3 plus 3 plus original 1. Totally we have 1 plus 9, that is equal to 10 structures. Now if I write this by replacing 1 hydrogen atom by CH3 group, like this. Now you remember, this carbon atom is not alpha, this is only alpha. It contains only 2 hydrogen atoms in the alpha position. This is actually ethyl benzene. We can expect only these 2 hydrogen atoms to give rise to hyperconjugation structures. That's why it will give rise to 1 plus 3 plus 3, totally 7. If you consider this CH, CH3, this is isopropyl benzene. This isopropyl benzene contains only 1 alpha hydrogen atom. That's why it will give rise to 1 plus 3. But if you consider this tertiary butyl benzene, like this CH3 thrice, this does not possess any hyperconjugation structure, because there is no any alpha hydrogen atom available in this one. That's why this tertiary butyl benzene is indicated only by 1 structure. So depending on the number of alpha carbon hydrogen sigma electrons, we have so many types of hyperconjugation structures. That's why among these, the most reactive is toluene, next ethyl benzene, next isopropyl benzene, next least reactive towards the substitution in the benzene ring is this tertiary butyl benzene, because due to the hyperconjugation structures, the negative charge increases in the ortho and para positions. That's why this toluene becomes more reactive in the ortho and para position as compared to ethyl benzene, which in turn is more reactive as compared to isopropyl benzene. And among all these alkyl benzenes, tertiary butyl benzene is least reactive. So this is all about the hyperconjugation effect and Baker-Nathan effect. One important point, in case of this hyperconjugation structure, the bond between this H plus and carbon is actually broken. There is no bond between this carbon and hydrogen. That's why this Baker-Nathan effect or hyperconjugation effect is also named as the no bond effect. So it is called no bond effect, Baker-Nathan effect or hyperconjugation effect. And since carbon, hydrogen, sigma electrons are involved, so this is interacted with this pi electrons. So it is also called as the sigma pi interaction. Sigma pi interaction. I will repeat. In case of the inductive effect, due to electronegativity difference, there is a polarization. Only sigma electrons are involved. In the electromeric effect, because of the need of the attacking reagent, there will be polarization of the double bond. It is a temporary effect. But in case of the resonance effect, interaction of the pi electron with pi electron in the conjugation or pi electron in the with the lone pair of electron in conjugation, so there will be polarization. But in case of this hyperconjugation, since sigma carbon hydrogen electrons interact with the pi bonds on the adjacent position, this is also named as the sigma pi interaction. It is a permanent effect. Among the various effects, only electromeric effect is temporary effect. The remaining three, inductive, resonance as well as hyperconjugation, they are permanent effects. So in the next video, we will go for the reaction intermediates. The reaction intermediates that we come across in various organic reactions are free radicals carrying the unpaired electron on the carbon atom. Carbon free radicals like methyl free radical, ethyl free radical, etc. Similarly, carbocations. Carbocations carry the carbon positive charge. Carbon ions. Carbon atom carrying the negative ion, negative charge is called as the carbon ions. And if two unpaired electrons are present on a carbon atom, it is called as a carbene. With suitable examples and relative stabilities, we will consider the various reaction intermediates in the next video. Thank you.